Hello students! So today we have another opportunity to sneak in another day with some other trigonometric identities, some of the identities that we would typically teach in a normal school year, and I thought I might have to skip over this year, but I think I can squeeze in this day. So just to keep my notes numbers all kind of where they're supposed to be, I'm going to call this one notes number 44.8. You might remember yesterday was 44.5. So then next time we're going to have notes number 45 and we're going to be back on track. And the double angle identities can be pretty quickly developed based on the angles or the identities we had yesterday. So I'm going to go ahead and show you where they come from. So remember yesterday we had the sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. So what if the two angles, alpha and beta, were actually the same? What if it was alpha and alpha, or beta and beta, or if they were both called something else, like theta? So imagine that we have the sine of alpha plus alpha. Then every time we see a beta, we're going to replace it with an alpha. So we have sine alpha times cosine alpha plus cosine alpha times sine alpha. Now when you multiply sine and cosine together, it doesn't matter if it's sine first and cosine second, or cosine first and sine second. So this term here is the same as this term here, and we have two of them. So we can rewrite this as 2 sine alpha cos alpha. Okay, so for our double angle identities, I'm going to make a box over here, and this is going to contain the identities that we're learning today. So you can use alpha, you can use theta, whatever. I'm just going to use theta. Sine of 2 theta is 2 sine theta cosine theta. Okay, now for the next one, if you wanted to remember from yesterday, the cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. So similarly, what if you had the two angles the same, like alpha and alpha? Replace all the betas with alphas. We get cosine alpha minus sine alpha sine alpha. And cosine alpha times cosine alpha is the same thing as cosine squared alpha. Remember, cosine squared alpha is the same as writing cosine alpha quantity squared, but we just don't write it that way with parentheses. We have our simplified notation instead. So we have cosine squared alpha minus sine squared alpha. And whether we use alpha or theta or whatever, it doesn't matter. So the double angle identity for cosine is cosine 2 theta equals cosine squared theta minus sine squared theta. Now that probably reminds you of the trigonometric identity that says sine squared theta plus cosine squared theta is equal to 1. So if I isolate cosine squared theta in this equation, cosine squared theta equals 1 minus sine squared theta. And if I substitute that into my other identity we just got, it'll change how it looks a little bit. Similarly, if we take our Pythagorean identity and we isolate sine squared theta, we get sine squared theta equals 1 minus cosine squared theta. And if we take that and we substitute it into our cosine double angle identity, we get something that looks a little different. So altogether, we come up with 3 different versions of this identity. So cosine of 2 theta could also be written as 2 cosine squared theta minus 1, and cosine of 2 theta could also be written as 1 minus 2 sine squared theta. So that just gives us some options. They'll all give you the same answer, but they are just slightly different ways to do it. Finally, to find the tangent of 2 theta, we can think of the tangent identity from last time. We had, I don't know, we didn't use it much, but I did mention it at the very end. We had tangent of alpha plus beta is tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. So if those letters are the same, if you have alpha plus alpha, replace all the betas with alphas, you get tan alpha plus tan alpha over 1 minus tangent alpha times tangent alpha. And so tangent alpha plus tangent alpha on the top is 2 tangent alpha. And on the bottom, 1 minus Tangent alpha times tangent alpha is tangent squared alpha. And then in my box here, I'm just going to write it with a theta in it just to be consistent. But again, it doesn't matter what letter. It's still the same identity. So what we'll do next is practice using these. Yesterday, when we learned the angle addition and subtraction identities, we did a lot of examples with numbers. For example, today, if we wanted to do one with numbers, maybe we would find the exact value of the sine of 600 degrees. And we could do that because we know that 600 is double 300. So if you're wanting to use double angle identities, think about what this angle is twice. So this is twice 300. So the identity, which says sine of 2 times an angle equals 2 times the sine of the angle times the cosine of the angle, would translate into 2 times the sine of 300 times the cosine of 300. And then from there, you could use reference triangles for 300 degrees. That would leave you with a 60-degree angle. Make your reference triangle. It's a 30, 60, 90. So the sine of 300 degrees is negative square root 3 over 2. And the cosine of 300 degrees is 1/2. So we have 2 times negative square root 3 over 2 times 1/2. You can cancel one of the 2's on the bottom with the 2 that's on the outside, and we're just left with negative square root 3 over 2. Now we don't typically do a lot of numerical examples with double angle identities because really there's an easier way to do 600. Remember coterminal angles? Coterminal angles have the same initial side and the same terminal side. So 600 is coterminal with whatever you would get if you subtracted one whole circle from it. If you subtract 360 degrees from it, you get 240. So 600 and 240 are coterminal. So you could just find the exact value for the sine of 240, and that would get you the same answer. So here's the kind of example we're going to do instead. Primarily, let's say it says find the sine of 2 theta if the tangent of theta is negative 4/3 and theta is in quadrant 2. We had an example similar to this yesterday as well. So you're given these clues about theta. Use those clues to make a reference triangle. So theta is in quadrant 2. That means the terminal side is in quadrant 2. So this is angle theta. The tangent is negative 4/3. So I'm going to put a 4 on the opposite and a negative 3 on the adjacent. So that means the hypotenuse is 5. So now we have our reference triangle, and we're going to find the sine of 2 theta. So first write down the identity. The sine of 2 theta is 2 sine theta cosine theta. So we have our 2. Then you look at the triangle. The sine of theta is 4/5. And you look at the triangle again. The cosine of theta is negative 3/5. 2 times 4/5 times negative 3/5. Multiply the numerators. Multiply the denominators, and we get negative 24/25. Okay, let's do another example. This time we're going to find the cosine of 2 theta if the sine of theta is 1/3 and theta is in quadrant 1. So we'll draw a reference triangle, quadrant 1, here's theta, sine is opposite over hypotenuse. So when you use the Pythagorean theorem, you get square root 8 for the adjacent. Now you could change that to 2 square root 2, but I'm going to leave it as square root 8 and then simplify later, and I think you're going to see why it's helpful to leave it like that. So we're finding cosine of 2 theta, and according to our identity, we actually have 3 choices. So one of the choices is cosine squared theta minus sine squared theta. Remember, when you see cosine squared theta, it means take cosine of theta and square it. And when you see sine squared theta, it means take sine of theta and square it. So looking at our reference triangle, cosine theta is square root 8 over 3. We're going to take that and square it. and sine theta is 1 over 3. We're going to take that and square it. Squaring the first one gives us 8/9. Squaring the second one gives us 1/9. So then we subtract and our answer is 7/9. Now let's just see what happens if we use one of the other versions of this identity. So how about if we use cosine of 2 theta equals 2 cosine squared theta minus 1. So we have 2 times, and still cosine of theta is square root 8 over 3. So we have square root 8 over 3 squared minus 1. And then when you square that, now we have 2 times 8/9 minus 1. That's 16/9 minus 1. 1 is 9/9. And 16/9 minus 9/9 is 7/9. So you see, same answer, different way to do it. And then the third one is cosine of 2 theta equals 1 minus 2 sine squared theta. Now there is actually an advantage to choosing this particular one if you thought about it ahead of time. The only thing you need to know is sine of theta, and we already knew it. We didn't even need the reference triangle to find the sine of theta. So if we do it this way, we have 1 minus 2 times 1/3, the sine of theta, squared. So let's go ahead and square it. That's 1/9. So we have 1 minus 2 times 1/9. So 1 minus 2/9. 9/9 minus 2/9 is 7/9. Okay, so usually you only have to do it one way unless the problem says do it all 3 ways. And if you do it all 3 ways, make sure you get the same answer all 3 times. And now let's do one final example where we're using the tangent identity. So let's find the tangent of 2 theta if the cosine of theta is -1/4 and theta is in quadrant 3. Okay, so reference triangle, quadrant 3, here's the terminal side. That whole angle is theta. Here's a reference triangle. Cosine would be adjacent over hypotenuse. Do the Pythagorean theorem and you end up with square root 15 for your opposite. And let's put a negative on there. So then, using the identity for tangent 2 theta, we're going to need 2 tangent theta over 1 minus tangent squared theta. So looking at the picture, the tangent of theta, negative square root 15 over -1, is positive square root 15. So we have 2 times square root 15. Don't really need those parentheses. I don't know why I put them there. Over 1 minus square root 15 squared. So we have 2 square root 15 on the top, and we have 1 minus 15 on the bottom. So we have 2 square root 15 on the top, and the bottom is -14. And we can reduce, and we get negative square root 15 over 7. Okay, so that's how you use your double angle identities. And your assignment is going to be another worksheet, fairly short, just so that you get a little practice with each of these. Thanks, everybody.